Hey, grade 9, so I'm going to go through topic 1 in electricity. It's static electricity. So first off, there are two general types of electricity. There's static electricity and then there's current electricity. The difference between these two is the flow of electrons. So if you think about, I'll do current electricity first. So current electricity, you can think about as, if you had a wire, and what's happening there, we'll talk more about this later too, is you just have electrons that are flowing through the wire. They're moving one direction, and that's what's powering your lights. That's what's powering your phone right now. That's what's powering this computer. The other type of electricity is static electricity. The word static means not moving. That might be a little bit of a misleading term, and I'll explain why. Static electricity, what that is if have you ever rubbed your feet across the carpet and then touched a doorknob or touched another person and you shock them? That's static electricity. Or lightning. If you're in a storm and there's lightning come crashing down, that's static electricity too. So it is kind of moving. You can see it, like, it moves. You can see the flash of lightning. You can see the spark go to the doorknob. So it's moving at that point, but right before it jumps, before it makes that electricity, like you kind of see right here, before it does that, it builds up. So if you had, let's say, like a balloon, and you had like a wall right here, and you rub the balloon all over the wall, you might be stealing some of that balloon's electrons. So, well, I'll explain more of this later, but what's kind of happening is that you've got a buildup of electrons here. So electron, 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 a bunch of them all on the balloon. And on this side, you have not very many electrons. So what's happening is that you get this buildup happening, and then finally it ends up shooting across. That's static electricity. So yeah, it's static before it jumps across, I guess you could say. A better way to kind of describe this would be a charge imbalance, because you've got a whole bunch of electrons here, which means you have a whole bunch of negative things and a whole bunch of more positive things on this side. So what you really have is a charge imbalance. If we could rename static electricity, charge unbalance or unbalanced charges, it'd probably be a better way to name it. All right. So electric forces. So what I mean by electric forces is this statement here. So objects with electric charge will try to have the same charge as objects around them. They do this by gaining electrons or by losing electrons. So what happens is that sometimes things gain a charge, and a good example of this is electricity, or is lightning. So if this is the ground and this is like my cloud up here, for things that happen in the air, like clouds, kind of different pressure systems and everything happening, what happens is you might get a buildup of electrons up here. I'm just drawing little negative symbols for electrons. And then down here you have the ground, right? So the ground is actually neutral, so we have the same number of positive and negative things, but it's neutral. But what happens is that all these extra electrons that are hanging out on this cloud up here, they want to balance the charges. They want everything to even out. So what happens is they get too many electrons, and then they jump down to the ground, and that's what you see as lightning. So this next slide, that's pretty much exactly what I was saying in the last one. So when that cloud ends up giving all of its electrons down to the ground, it ends up having electrical discharge. So there's another term that we need to know. Electrical discharge just means that the moving of electrons. Okay, just a little need to know thing. You know how I was saying when you rub your feet on the carpet, you can shock people? Electric eels pretty much do the same thing, but they just get that buildup internally, like inside them. They produce static electricity that builds up, and then when they need to protect themselves, they discharge that. So the same thing as you rubbing your feet on the carpet, they just do it much better than you do. Okay, so just common ways to draw these things. We've got three types of charges, definitely need to knows. You can have a neutral charge, a positive charge, and a negative charge. neutral charge is more typically kind of drawn like this. You can see that I've got 5 negative symbols or negative electrons, right? 5 positive things. Those would be like the protons, or they are the protons. And they're equal, right? Neutral charge means that they're balanced out completely. By the way, what things do you think move? Electrons or protons? It's the electrons. Because if you think about your, atom that you had, right? Let's say you've got like, a couple protons, and then you got like, some electrons around the outside. The electrons are the ones that are able to move from one thing to the other, right? So they're the only thing that can move. Protons don't move at all. Lightning isn't a bunch of protons, positive things shooting to the ground. It's just the electrons. They're the only things that can move. That's a big aspect to this, is knowing that protons can't move. It's the electrons that move. So you can see if we go down to positive charge, what's happened to make this cloud, let's say, positive, is that it's lost 2 electrons. So now it's positive. You can see that there were 5 to begin with, and there's still 5. The protons stay the same. The electrons are the things that are moving. So now it only has 3 electrons. So overall, it has 2 more protons, so it's positively charged. But again, it's the electrons that move. That's the important bit. So negative charge, that means it's gained more electrons. You can see it still only has 5 protons, or 5 positive charges, but it's gained negative charges from something else. Okay, 3 laws of electric charges. This is also important. So opposite charges attract each other. This shouldn't be anything new. Well, it might be new for this, but you guys all know that if you have magnets, that if you have a north pole and a south pole, they attract, right? We've got the same situation here, but instead of north and south, we're going to have, if you have a positive and you have a negative, they're going to attract. And just like magnets, let's say if you had a north pole of a magnet and another north pole of a magnet, they're going to repel each other. Well, you've got the same thing with charges too. If I've got a positive charge and a positive charge, they're also going to repel each other. So nothing really new there. So it's just saying opposites attract, just like magnets. Like charges repel, just like magnets. And then charged objects attract neutral, uncharged objects. That's the only kind of thing that's kind of new here, because magnets don't do that. Like a north magnet doesn't attract something that's like, not metal or something like that, right? The reason for this, you just really more than anything need to know that this is true, but I'll show you why that's true. If we've got, let's say, some charged object, let's say it's negatively charged. It's got a whole bunch of electrons, right? And we've got this object that's neutral. So originally it's got, evenly spaced out negatives and positives. Those should be evenly spaced out. And this is saying that they should be attracted to each other, right? Well, the reason for that is because this is really negative, right? This thing's really negative. What happens is that the different charges inside this thing kind of rearrange. The protons don't move, remember, so they all stay exactly where they were. But what happens is that when this thing comes close to this other thing, these electrons push the other electrons in this neutral object over to the right side of this thing. And then what's left is I've got mostly positive on the left side. Now they're going to be attracted. So that's why number 3 is true. Hopefully you can kind of see what I mean there. I'll help you out in class if you don't. More than anything, you just need to know that this is true for grade 9. If you get into physics, then we'll talk a lot more about why this picture I drew is true. All right, moving on. Actually, I'm going to end that video right there. I'm going to pick this up in a new video. So I guess I'll see you guys in the next video.